And finally, here's Part C of the 2018 Regents exam. And again, you should be answering this in your answer booklet, not directly on the test like I am doing, right? So anyway, let's wrap this up. So we have ourselves a bulb here, and it says incandescent light bulb uses a length of thin tungsten wire as the filament, the part of the bulb that produces light. One bulb is a 0.22 meter length of the tungsten wire used as the filament. The wire filament has a resistance of 19 ohms at 20 degrees Celsius, which is room temperature. That is the reference temperature for the resistivity chart on page 4 of the ref tab. And tungsten wire filament has a resistance of 240 ohms when the bulb is operated at 120 volts. So then 6667, calculate cross-sectional area of the tungsten wire filament. Alrighty, so for this guy, I'm going to use the equation resistance is resistivity times the length over the cross-sectional area. And it says I knew the resistance at 20 degrees Celsius. That is the room temperature. That's the reference temperature for the resistivity of tungsten. So I'm going to use the 19 ohms here for R, and it's when the resistance is 19 ohms, the resistivity is 5.6 times 10 to the negative 8 ohm meters. And then the length is given as 0.22 meters, and then we're trying to solve for the area. And so when we go and work the numbers and solve for the area, we get 6.5 times 10 to the negative 10 meters squared as the cross-sectional area. Very thin wire, very small cross-sectional area. Now the reason why we're using the 19 ohms and not the 240 ohms is because the resistivity of tungsten is 5.6 times 10 to the negative 8 ohm meters when at room temperature. But when it's operating at 120 volts, it is not room temperature. In fact, it is white hot, which is why it produces light. So anyway, that is the cross-sectional area no matter what. In fact, it says why the resistance of the tungsten wire filament increases when the bulb is being operated compared to the resistance at 20 degrees Celsius. And yeah, when operating, the current through the filament greatly increases its temperature. And an increase in temperature is going to increase the resistivity, and an increase in resistivity will therefore increase the resistance. Now, 6970, calculate power when operated at 120 volts. And I don't actually know the current at 120 volts, but I do know the resistance, and it's a 60-watt light bulb. Don't forget to square the voltage. All right, and again, a reminder that for questions that are 2 points, you need to show work, including an equation and unit substitution. All right, so that's our light bulb situation. Let's move on for 71 through 75. So we have a crate being pulled on a wood floor by a force at an angle 30 degrees, 150 newtons, applied to a wooden crate, horizontal floor, constant velocity. This tells me that the net force is 0. Of course, the horizontal wooden floor is represented below. What is the horizontal component of the 150 Newton force? Gosh, I wonder why they might want that. Well, let's find it. So, any x component uses cosine. Fx equals f cosine theta. Of course, be in degree mode for this. And so we get 150 newtons times the cosine of 30 degrees, and we get 130 newtons. Okay. Then 73, what is the friction force acting on the crate? Well, let's see, FF is mu Fn, and I do happen to know that it's wood sliding on wood. Great, so I can look up the coefficient. There's only one problem. Normal force, when I'm not on a ramp, is equal to weight, which is equal to mg. Well, guess what? I don't know what the mass is, and I don't know what the weight is. So actually, I can't use this approach at all. Instead, I have my backup equation for friction. Net force is push minus friction. And I noted earlier, because we're at constant velocity, the net force is 0. And so the pushing force, F push, put in 130 newtons, minus the friction force, and so the friction force, therefore, FF is 130 newtons. Oh, but wait. Why isn't it 150 newtons? Isn't that what the pulling force is? Like the F push in this case. Yes, except that friction is acting parallel to the ground. And the friction is going this way, but the F pull is going up at an angle. And so the only thing, like in terms of that the friction is opposing, is the Fx that we calculated in 71, 72. That's why they had us find it, right? And so that winds up being 130 newtons. And in order for the net horizontal forces to be zero, if the x component of the force is 130 newtons, in order to balance that out, the friction force must also be 130 newtons. And so there that is. If you said 150, I mean, it's only 1 point, so not the end of the world. Now it says find the normal force. Now this is interesting. Now that I know the friction force, and I do know the coefficient for its sliding of wood on wood, now I can solve for Fn. And we said before that equation doesn't work because I don't know Fn. Right, well now I know the friction force and I know the coefficient. I can solve for Fn. I believe the coefficients of friction are on page 1 of the ref tab. And if I divide both sides by 0.8, or 0.3, I get 430 newtons for my friction force. Of course, this is error carried forward from number 73. All right, let's keep going. We're getting close to the end. 76 through 80, all of these questions are based on this description. 1,500 kilogram car, so I know the mass. Travels around a curve with a constant radius of 45 meters. I know the radius. Centripetal acceleration, AC, is 3.2 meters per second squared. And it says find the speed as it travels around the curve. Well, I know that centripetal acceleration, speed squared over the radius. I can put in my centripetal acceleration of 3.2 meters per second squared is speed squared over 45 meters. Therefore, speed squared is 144, so the answer is 144 meters per second. But wait, the number one careless mistake in mathematically speaking on the Regents is forgetting to square or square root. And so the speed is not 144, it is 12 meters per second once you square root that 144. Okay, terrific. Now, what is the centripetal force as it travels around the curve? That's not tough. We can just do F equals ma, Fc equals mac. 1,500 times 3.2 is 4,800 newtons. Then 79, what force provides the centripetal force needed to travel around the curve? And so gravity does help, but it's not in orbit around the curve. I would say it is the tires on the road, but we need to be more specific. Tires on road is not a force. What force is that, the tires on the road? It is, of course, friction. It's actually static friction that's doing it. Because if it were kinetic friction, the tires would be skidding instead of sticking. This tires stick to the road, so that's static friction. Saying it's friction is sufficient. I'll put in parentheses static. But just saying friction is good enough. All right, then 80. What happens to the centripetal force on the car as it travels around the curve if the speed decreases? So I know that centripetal force is mac, and ac is v squared over r. So when you combine their powers, they become fc is mv squared over r. And it said if the speed were to go down, then the centripetal force would go down, because centripetal force is directly proportional to speed squared. So if speed goes down, if speed decreases, centripetal force decreases. In fact, it decreases by a lot because speed is squared. So whatever happens to speed, the centripetal force is thus affected a lot. Okay, terrific. We have the last question set. We have ourselves a acoustic guitar with a string that's vibrating. It looks like it has a node in the antinode in the middle and nodes at the ends. And it says the length of the string is 0.620 meters. And then it says it plays the G note, and that's a frequency of 196 hertz. 81, identify the node in the antinodes. The nodes are always at the walls where we have no motion. So we have nodes right there, and then in between the nodes, we have ourselves the antinode, the point of maximum constructive interference where we get the most vibration. So that is 81. Then 82, what's the wavelength of that standing wave? It's actually going to be twice the length of the string, and I can show you why. Let me just redraw this diagram. So we have wall, and then we have nodes on the end, and then we have the antinode in the middle. But that's only one part of the full cycle. Nodes are half a wavelength. Nodes are half a wavelength apart. I mean, we can see that from one node to the next node, that's only half the full wave. So if I have 0.620 meters is half the wavelength, then the wavelength is 1.24 meters. And now that I know the frequency, the 196 hertz is the frequency, and the wavelength, calculate the speed. V equals F lambda. Let's go, buddy. 196 hertz. Wavelength is 1.24 meters. Error carried forward on that, of course. And we get 243 meters per second. So 243 meters per second. That is the correct answer. Then finally, 85, what happens to the frequency? The musician shortens the vibrating portion of the string by pinching the string against the fingerboard while the string continues to vibrate. And again, this says describes, you don't actually have to explain it, but since V equals F lambda, and the speed is constant because it's the same medium being this string, the frequency is inversely proportional to the wavelength. So by pinching the string higher up the fingerboard, giving less of a wavelength for the standing wave, as wavelength decreases, the frequency is going to increase. It's going to be a higher pitch. And that, so you don't even need to explain that. You can just say that the frequency would increase. All right, and that's it. That's the end of part C. That's the end of the 2018 solutions. Thank you.